Okay, we're going to take a look at the properties from the last video, and I'm just going to do some numerical examples of each. I was originally going to do this in the last video, but Mr. Pansioko came to say hi, and I cut that video a touch shorter than I wanted to, but that's okay. So now we'll just take a look at a few examples in this extension video. So the first one, log base anything besides 0 of 1 equals 0. So if I saw some random example, log base 93 of 1 equals r. Now clearly I want to actually encourage you guys that if you don't memorize all of these, and that's okay, that you at least apply this definition, and you can probably deduce these properties if you happen to forget them. So applying this definition to this problem, 93 is the base in exponential form. The answer in exponential form is 1, and the exponent in exponential form, that's going to be this variable r. The logarithmic expression itself is basically the exponent. And then hopefully you remember, I hope, that some non-zero number raised to the 0 power will always equal 1. So r equals 0. Any log, any base of 1 will always equal 0. And that is because, of course, once again, any positive number raised to the 0 power, any non-zero number, I should say, not necessarily positive, but non-zero. Any non-zero number raised to the 0 power is always 1. Okay. An example for this next lovely property of logarithms. Here, when you have the log of the base of some number, in this example I'll just choose 37, and then the number at the end of the log expression is the same number as the base. This is effectively asking you, when we apply this definition, 37 raised to what exponent power equals 37. And when you put it in this form, hopefully you remember that any number is basically itself raised to the first power. So because that question mark is 1, log base any number of that same number is always equal to 1. All right, numerical example for this next log property. If I had log base any number, I don't know, I'll choose 17. 17, that same number, raised to some variable, I don't know, I'll make up r, why not? So when we happen to notice, very, very similar to this rule beforehand, only this time we got another exponent here at the end. So the property is going to tell us, hey, this is just going to be r. If you forget the property, we use our lovely definition and derive the property. So the definition says, in case you forgot, there it is. The definition says 17 is the base. It is going to be raised to the power of something. And the answer is going to be this expression here at the end, 17 raised to the power r. And once you convert it to exponential form, hopefully it's very obvious. 17 raised to what power equals 17 to the r? Well, that's just plain old r. And we actually have this other version of basically the same inverse property here. Let me choose some other random number, 35 raised to the power of log base 35. Q equals question mark. Oh, I don't know, because I forgot this property, but I remember my definition, so I will apply my definition and derive the results. Sorry, a little disorganized. So this is, once again, this is sort of already in exponential form. I know it might be a little confusing because it says log here, but that's an exponent itself. So 35 is the base. Let me rewrite this as a logarithmic expression. Log base 35 of question mark equals log base 35 of Q. And when you convert it to this form, hopefully it is very obvious the only way that this statement is true is if question mark equals Q. And the final property from that last video, the one-to-one property, log base whatever number of one value equals log base of that same number of another value. That would only be true if those two values at the end equal one another. So as a quick little numerical example, just make some random thing up here. Log base 7 of 3 equals log base 7 of x. Applying the logarithm definition, 7 is the base. The exponent power is log base of x. The answer is 3. I don't know if this is the most efficient way to explain this. I almost ran into a property that I have not showed yet. It's going to come up in another video. So let me actually just let me try a different strategy real quick. Sorry about that, friends. We'll set this equal to R and this equal to Q. Basically kind of take a look at half of this equation at a time. So on this side I have 7 raised to the power of R equals 3, and on this side I have 7 raised to the power of Q equals X. However, R and Q have to equal each other, so I can replace because of the condition I set up over here. So if I can replace this Q with the R, I get 7 to the R equals X, but here 7 to the R equals 3, so the only way that this would work is if X equals 3. Sorry. I will, in a video coming up very, very shortly, talk about the property that I almost wanted to talk about with this problem here. We'll get to that soon.